Hello, Mitch Kitchen, Cobleskill, Richmondville High School Technology. Today we start our study of simple machines, and we're going to begin that by looking at levers, specifically first-class levers. Now, simple machines are used all over the place, and they're useful for changing the size or the direction of a force. They can increase or decrease the amount of force, and they can also change its direction. We take a look at a picture of a first-class lever, a simple lever. This would be something like a teeter-totter. And the fulcrum is the point about which the lever pivots. And then we have a couple forces on the top. This is the resistance force, this is the effort force, and then we have two distances, the resistance and the effort distance. The mechanical advantage is the amount that a machine multiplies a force. Now we say multiplies a force, note that this number can be less than 1. So the simple machine can actually reduce the amount of force as well. And there are two calculations that you'll need to be able to do for mechanical advantage. The first is the ideal mechanical advantage, and that is just the ratio of the effort distance divided by the resistance distance. Now, because these are distances, we're not worried about any friction, so this is more of a theoretical calculation. That's why it's the ideal mechanical advantage. The actual mechanical advantage is the ratio of the forces, and notice that it's resistance force now on top and effort force on the bottom. You divide those two, and that will give you the true mechanical advantage of the system, and that accounts also for the frictional losses that take place. Now we can take these two ideas about ideal mechanical advantage and actual mechanical advantage and put them together and come up with an equation of static equilibrium. Equilibrium means balanced forces, so this is a balanced force equation, and one way to write it is with the effort and distance on the same side, the resistance, forces and distance on the same side. If any of you have taken physics, specifically Honors Physics Symposium, you will hopefully recognize these as torques. We'll be talking about torques later on in this course, but a force times a distance, if we look at those as vectors, gives us a twisting force. And so what we're saying is the twisting force on each side is essentially balanced. So we can take these two, you can write the equation like this, but generally, because we're going to be given ideal mechanical advantage, actual mechanical advantage on our reference table, we just put those two together, and we can say dE over dR is equal to FR over FE. Now here's a quick example of a first-class lever system. So we start over here on the left, we have a resistance force of 70, and that's lbf, pounds of force. Over here on the right-hand side, we have a 10-pound effort force. And then we have 1.5 feet over here. This will be my resistance distance because it's from the fulcrum to the resistance, and I don't know what the effort distance is yet. Two things that we're going to take a look at. First, we're going to find the actual mechanical advantage. And this is the way you're asked to solve problems in a Project Lead the Way type course. They're asking you for formula, a substitution, and a result, and we put these little vertical lines to separate those. So I begin with the equation. The actual mechanical advantage is the force of resistance divided by the effort force. Now we put in the actual numbers. That's 70 pounds of force divided by 10 pounds of force. The decimal point over here means that I've measured these out to two significant digits. So I'm going to give my answer to two significant digits. The actual mechanical advantage is 7.0. We'll talk more about significant digits in class. The second thing that we're going to do is find the effort distance. And here I'm going to be using the equation of static equilibrium, because if you take a look at this, the only thing that I don't know in this equation is the effort distance. So I put in the forces, and note when you put in the distance to the resistance, I'm writing down the actual units. When we're using dimensioning, we can use the little hash marks or tick marks to indicate feet, or two tick marks to indicate inches. But when you're using an equation, we like you to write out the actual notation for the unit, so over 1.5 feet. Now to solve this, we typically cross multiply, so I multiply 1.5 times 70, then I divide by 10. When you do that, you come up with 10.5 feet. but I have 2 significant digits in each one of these numbers, so I round my answer to 2 significant digits, and we say the effort distance is 11 feet. We'll be doing more problems like